to monitor the camera. But I appreciate it when you do.
So just a clarification, so the pi bonds and the lone pairs are for the resident structures and
You will only need to consider them. Yeah, I will come back, ask that question again, but that is actually why I'm doing all this.
okay.
So the first bond you're going to get, and so here's the takeaway that I want you guys to get for this. Every bond, right? So a bond, two shared electrons. Where do you keep it? So the two shared electrons are in a bonding molecular orbital. So if you see a bond, that's two electrons, it's two bonding electrons in a molecular orbital. Every bonding molecular orbital has an anti-bonding molecular orbital corresponding to it. And that's usually going to be empty. It's an anti-bonding orbital. If we're talking about a molecule that exists, right, there's not going to be antibonds. So, however, the antibonding orbitals turn out to be important for most chemical reactions. Think about it. A chemical reaction happens when we make or break a bond. Bonds are electrons. So chemical reactions involve electrons changing molecular hands. If molecule A wants to put electrons into molecule B, right, they've got to go somewhere. Molecules are tiny. They don't have, you can't, if I want to give you $10, I can just hand you a $10 bill. You can hang on to it. You can put it in your pocket, put it in your shoe, put it in your mask. People carrying money around a mask? That's got to come next, right? But you can keep it anywhere. You could put it in your bank account. The only place a molecule can put an electron is in a molecular orbital. So if all my bonding orbitals are filled and I get some electrons, I'm going to put them in an antibonding orbital. So the antibonding orbitals become important when we talk about chemical reactions. Right now, all you guys, and really for this entire class, all you have to know is that a bond are two electrons in a bonding molecular orbital, and that every bonding molecular orbital has a corresponding antibonding orbital. Yeah?
So when a bond is broken, do the electrons go into the antibonding?
It depends. It depends whether, so a lone pair, let's go back to lone pairs. All these lone pairs are non-bonding, and they don't have a corresponding antibond. So like if a reaction happens and a bond breaks, it could be that the electrons go into an antibonding orbital. They could just become lone pairs as well. Okay, so this is a sigma bond. I'm going to raise this up. Let me raise it up over here. Every bond is a sigma bond. All right, that's the beginning. So in water, the two OH bonds are sigma bonds. Single bonds are always sigma bonds. The sigma bond is directly between the two atoms, right? This is like a hydrogen nucleus there, a hydrogen nucleus there, and the sigma bond sort of is cylindrical and takes in both nuclei. It's really like a handshake, right? So we shake hands. That's a strong bond. Now, the way quantum mechanics works, you can't have other orbitals in the same place. All right? So once we make one sigma bond, that's all the sigma bonds we can have. A second bond has to be elsewhere. Okay, so there is, actually let me do oxygen. So let's do the carbon-oxygen double bond. I don't like this math. All right, so they make a sigma bond. Again, first bond two atoms are going to make is a sigma. Every other bond after that's going to be a pi bond. Pi bonds are weaker than sigma bonds by about 60%. Sorry, 40%. Right, again, this is going to be the same sort of thing. So the carbon is going to have one p orbital. The oxygen will have to have one p orbital. So if you see if you see any second row element make a double bond, if it makes one double bond, it's going to be an sp2 atom. So it's got to have one p orbital to make the double bond. And these need to be in phase. Again, if you look at the mathematics of a p orbital, then what am I trying to say? You get to a square root, right? So what's the square root of 4? 2, right? Is that it? Is that the only square root? What's the other one? Right. So you get down to like the square root of some very long equation. The positive is the upper lobe, the negative is the lower lobe. Right? So these come together, two positives reinforce. To get the p orbitals, right? The p orbitals are lobes above and below. There's a node at the nucleus. And so to get those to overlap constructively, they have to come together a little closer. Right? If I shake hands with you, and I didn't actually do this before COVID. Wake Forest frowns on me like hugging students. But a handshake, right? That's a firm business embrace. Right? You don't do that formal handshake with people closer to you. Right? You hug them. Right? To hug each other, you have to get closer. Right? So we can handshake from a distance. Again, we can't now. But if you're going to hug somebody, and that's a lot of the point, you get closer, right? So for these two atoms to make a double bond, they have to move closer together. So you wind up with that double bond is going to be shorter, and you sort of have bonding orbital density above and below the plane like that. And again, there is an antibond, there's a pi antibonding orbital that doesn't get electrons. Question? All right. So that's a pi bond. Now, almost done with resonance structures. Anybody know what that molecule is? I probably shouldn't ask this. No, nobody's saying it. That's good. So either you're shy or you don't know. Either way is fine. This is acetic acid. You guys don't need to have like some catalog of molecules memorized. All right? Like that's not memorization. How many of you have heard that organic chemistry requires superhuman feats of memorization? How many people are not admitting it to me that you've heard this? All right. You're going to have to memorize quite a bit of stuff, all right? I would love to tell you there's no memorization in this class. Memorize as little as you have to. Okay, memorization is tough. You guys, I will say this over and over, every generation treats the generation that comes after it, or the two, badly. It's just what humans seem to do. It's envy. I can say this from a relatively advanced age now. We're mostly jealous of you guys. You feel good, you have energy. So anyway, we're all people, right? Like, people are people overall. But the culture, the environment, the society you grow up in influences you. My generation didn't memorize stuff as well as the generation before mine because, you know, we had more technology. I could look stuff up. You guys memorize stuff less well than we did because not only can you look stuff up, you're actually carrying around what in 1990 would have been a really powerful computer. You know, you treat it like a soft drink. Okay, so you can look stuff up. You don't have to memorize as much. But memorization is actually important. You may have heard, like, I don't know if you have a great-grandparent or a grandparent that had to memorize poetry as a kid. Like, the reason they did that, it took me forever to understand this, wasn't because it's important that we all know poetry. It's because it's really good training to memorize stuff. And if you can't just immediately look a bunch of things up, you need to be able to memorize stuff. So in this class, it's some balance. You need to learn principles, but you need to have enough information stuck in your head that you can, like, use those principles on the information. Okay, so it's fine if you don't know this is acetic acid, and you don't have to memorize that this is acetic acid. What you do have to memorize is this functional group, which is called a carboxylic acid. I'll give you shortly a list of functional groups that you'll have to memorize. All right, so acetic acid is in vinegar. It's the ultimate product. If you drink ethanol and alcohol dehydrogenase oxidizes that up, you get acetic acid. What I'd like you to do now is draw a resonance structure, or two if you like, of acetic acid. Sorry. And this is going to come back to your question. About Okay, so the simplest thing, and I should say, I don't know where to put it. Green's bad. A carbon-oxygen double bond like that is called a carbonyl. That's also a nice thing to commit to memory. And there are lots of carbonyl compounds. Right? Carbon dioxide has two. Carbonyl there, carbonyl there. Acetic acid has one. And so the simplest thing when you have a pi bond, and so this gets to the question of why do you need pi bonds and lone pairs and charges to draw resonance structures? And really the way to think about this is you need to think about resonance structures when you see molecules with pi bonds and charges and lone pairs. Okay, so water's got some lone pairs. So maybe you think about it. But again, you can't break atoms apart. And what that means is you can't break a sigma bond. Right? The sigma bond forms first. I erased my pi bond, but every bond, if you see a single bond, it's a sigma bond. If you see a double bond, it's a sigma and a pi. If you see a triple bond, it's a sigma and two pi's. Right? You can never break the sigma bond. The sigma bond is the strongest, the more stable. Most stable. But you can break a pi bond. Right? If I move the pi electrons, I'm not changing how the atoms are bonded. So the simplest thing with a pi bond is just, bang, I'll pop these two electrons up. They'll become a lone pair. These two electrons stay the same. And again, you can run through that. A carbon with 3 bonds and no lone pair is going to be positive. We looked at that last week. An oxygen with 1 bond and 3 lone pairs is going to be negative, hydroxide. You can also use the calculation, neutral oxygen sharing 2 electrons, all of a sudden it takes sole possession of those electrons, it's going to become negative. Right? If a neutral atom gains electrons, it becomes negative. Neutral atom gives away electrons or loses electrons, it becomes positive. All right, so this is a resonance structure. Easiest way to draw the resonance structure. Note, there are 3 hydrogens on this methyl group. They're all sigma bonded. It's not a resonance structure if I take this H and I move it to that carbon. Right, I've changed the connectivity in that case. All right, there's another thing you can do here. Try that purple. Well, actually, now you've got an oxygen with a lone pair next to a carbon that doesn't have a full octet. Right, this positively charged carbon no longer has a full octet. It's got 6 electrons. There's no lone pair there. 1, 2, 3 bonds. 3 times 2 is 6. That carbon only has 6 electrons. So we can take 2 more. And in fact, either one of these lone pairs on this oxygen can make a pi bond there. When it does that, neutral oxygen gives away electrons, so it'll become positive. The oxygen has 3 bonds and a lone pair, so that's like H3O+. Positive carbon gains electrons, it'll become neutral. So the purple structure is also a resonance structure. Yep.
Can you just put the negative formal charge on other oxygens there?
Sorry. Oh, yeah, I didn't. You guys, many of you in here will at some point come to my office or on Zoom or whatever and tell me you just made a dumb mistake. And I will be sympathetic. I will still take the points away. Because I'm old and a jerk and I'm envious of your stamina. But, no, you need to, that's the thing. I tell students, you're not going to ace this class. There's all this stuff going on. Right? The more complicated things become, the harder it is to be perfect. And I don't ask you guys to be perfect. I ask you to learn. You're all going to make stupid mistakes, right? The reason I'm talking about this right now is I just made one. I went too fast. I'm thinking about other stuff. You got to focus. I'm up here. I'm thinking what I'm going to do next. I don't write the negative charge down, right? If you don't indicate a formal charge, it's an incorrect structure. So what I had drawn here, I've left off a formal charge. The beginning of the semester, I'm not going to take as many points off for that kind of thing. By the end of Orgo 2, that's like a huge deduction. The other thing is, this is now not, but it is a resonance structure because I've stupidly I've drawn the lone pairs. So if you draw those 3 lone pairs in there, I'm like, you know where the electrons are. But let's say I don't put the lone pairs there and I don't draw a negative charge. Right? It's not a resonance structure anymore because the charges aren't the same. This is neutral, that's +1. So they aren't resonance structures. All right, thanks for catching that. Always write your formal charges. The other thing, when we start doing chemical reactions and I ask you to draw mechanisms, if you don't draw the charges, you get really screwed up. Because you'll think atoms are there that aren't there, you'll forget where electrons got to flow and whatnot. So make sure you get those structures. Now, you could go from the original structure to here in one step. Right? I could just do also, I'm going to stop drawing all the dots sooner or later. Right? You could have gone immediately to that structure and it would have been fine. So, of the 3 structures up at the top, which one's better? All 3 together?
Like all.
Yeah, all 3. Compare all 3 of these. Which one do you think's better? Yeah, sorry. So this one, and here's a tip. The way we usually draw the structure is going to be almost always the best way to draw the structure. Right? All the atoms have a full octet. They're all neutral. So now you say of the other 2, this one's better. Anybody disagree? You disagree?
I don't disagree. The green, how come there's 2 arrows and then you didn't draw it on the purple diagram?
So the 2 arrows are lone pair here makes a pi bond to the carbon, pi bond on the here goes to the oxygen. If you follow this arrow makes the pi bond, makes that pi bond. This arrow breaks this pi bond and makes that lone pair.
Oh, okay. I see.
Yeah. What do you guys think? Blue or purple? A lot of blues. Why is that? Charges are closer. Charges are closer. If an atom must lack a full octet, better if it's the less electronegative. All atoms with a full octet. All right. So again, here you've got conflicting information. Blue is fine. Blue and purple both do a good job of representing the real molecule. Charges are closer. All atoms have a full octet. The other thing is these resonance structures indicate why acetic acid is so acidic. Right? Think about that H. It's now bonded to an oxygen that's fairly positive. And what that does, basically the carbonyl is pulling electron density out of this OH bond toward itself. It makes that H way more partial positive. We'll talk about acid-base chapter 3, but resonance structures are important. All right? So, that pretty much wraps up resonance structures in chapter 2. I'm going to move on for a second, but I'm going to say, I put this up at the end of the last class, draw a resonance structure of this molecule, and I'm going to leave that here. I will put that up online, the various resonance structures. Finally, to finish off, I had a question about this thing I said about sigma bonds. If you look at what you need a pi bond, because that pi bond lets you move the pi electrons without breaking connectivity. Or you need like a lone pair next to a positive, a vacant orbital. Right? If I've got a lone pair next to a vacant orbital, I can move the lone pair. Or I could have a lone pair next to a pi bond. Then I can move the lone pair to make a new pi bond, break the old pi bond, and move it. Right? So you generally want to look for pi bonds, charges, and lone pairs being close together so that you can move electrons. Because that's all you're doing in resonance structures, you're moving electrons. And it's why water doesn't have any resonance structures. I can't take the lone pair and put it on hydrogen. Hydrogen doesn't have any electrons to make a pi bond. If I break this OH bond, I'm doing a chemical reaction. That's not a resonance structure.